remember, in the last video, we talked about what relations were. Now, obviously, if there's a topic, then there are questions related to it. Today, we are going to be focusing on that. Let's do exercise 1.1 of the NCERT mathematics, and let's get through that because the NCERT questions are the most important type of questions for the board. Let's go through that. I won't be doing all of the questions, but you're free to ask your queries in the comment section. I'll be sure to rectify them in the next video. Apart from that, I will only be doing a certain set of questions with varying different types. And if you have any doubt related to them as well, you can ask your questions. Feel free. Let's start. The first question, open your books to page number 5 of the NCERT. The first question that is there is we have to determine whether each of the following relations are reflexive, symmetric or transitive. Giving a brief recap of the last session, we discussed what reflexive, symmetric and transitive relations were. I am sure you remember them. If you don't, go and watch the last video and then come back to this video for the questions. So, our first relation is defined for the set A, and our set A is 1, 2, 3 up until 13 and 14. Our relation is defined as R equals to x comma y ordered pair such that 3x minus y equals to 0. That is our relation. We have to prove or we have to check if these relations are reflexive, symmetric or transitive. Now, I will be solving these questions according to the pattern of the board. So, even if you're not noting down the answers, note down the pattern of solving the question because the step marking that is involved in the process of checking the answers for the board is important as well. We have to think about that too. So, this is our relation, this is our set on which the relation has been defined, and we have to check whether it is reflexive, symmetric or transitive. Let's begin with the reflexive. The domain of the relation over here has been specified. This set is the domain of this relation. So, first let us form the relation. We have 1 up to 14 numbers in the set A. So, if we have to form a relation which satisfies the condition 3x minus y equals to 0, then we need then it can be easily said that y is equals to x by 3. So, first up, if we take 1 as a number and then we have to write y equals to 1 by, then x or y over here would be 3. So 3 into x, which is 1, and y, which is 3, equals to 0. That satisfies the condition. So we can write r. We can first write r equals to 1 comma 3. If we go for 2, then if x equals to 2, let us write it in a simpler way. If 3x minus y equals 0, x equals to y by 3 or y equals to 3x. Both of these conditions, if you can fulfill them, you find your number. So the first element or the first order pair that we have for our relation is 1 comma 3. Next up, if we take the element 2, then y equals to 3 into 2, which is 6. So we get the ordered pair 2 comma 6 as our second element. The third number 3, if we take that, then y is equals to 3 times 3, which is 9. So we get our third ordered pair, which is 3 comma 9. The fourth ordered pair, if we take the fourth element, which is 4, the fourth ordered pair that would be formed would be 3 times 4, which is 12. So y equals to 12. Our domain is up to 14, and if you take the next element 5, then y is equals to 3 times 5, which is 15, which does not lie in our domain. So our relation ends here. This is our relation. Now, for reflexivity, what do? We check if the same element ordered pair is in our relation. If you can see in this relation, neither 1 comma 1 nor 1 comma 2 comma 2 and nor 3 comma 3 are present, neither 4 comma 4. None of the same ordered pairs are present in this relation. that denies it being reflexive. So R is not reflexive since neither 1 comma 1 belonging to R, or even if you write this condition, it is enough. If you want to write another condition like 2 comma 2 not belonging to R or 3 comma 3 not belonging to R, you can write so. But this simple little condition is enough for the exams. Let's check the symmetry of the relation. Here, if you look at it, 1 comma 3 belongs to R, but 3 comma 1 does not belong to R. It is nowhere in our relation. You can check it with another ordered pair. 2 comma 6 belongs to R, but 6 comma 2 does not belong to R. It is not present in our relation set. That ruins the symmetry of the relation. The relation is not symmetric. So, you will be writing R is not symmetric since 1 comma 3 belonging to R, but 3 comma 1 not belonging to R. This simple condition is enough, but if you want to write it for the other ordered pair elements, you may do so. It is up to you. Let's go on and move up to the transitivity of the relation. Now, for transitivity, our condition is that if we take two ordered pairs A comma B and B comma C, then A comma C should also be belonging to R. So, first, let's see. We have 1 comma 3 belonging to R. Okay, and we have 3 comma 9 belonging to R. Right? But we do not have a 1 comma 9 belonging to R, do we? So, you will be writing R is not transitive since 1 comma 3 belonging to R, comma 3 comma 9 belonging to R, but 1 comma 9 not belonging to R. Now, after you have proved that all of these are neither reflexive nor symmetric nor transitive, there is one statement that you need to write, which is what I just said, that relation R is neither reflexive nor symmetric nor transitive. This is one statement that you need to write, because in the question it is stated that determine whether the given relations are reflexive, symmetric or transitive or not. So you need to state whether they are or whether they are not, and you have to specify all three conditions. Now, all of the other questions in this part are similar. I will do the fifth part as well for this question, which is, as you can see, for the fifth part of this question, there are 5 subparts to this question as well. I won't be doing all of them because we need to work within some time limits. And let us begin the question first, and I'll see which parts I have to do. So, the question 1, fifth part, the A or our set has been defined as the set of human beings in a town at a given particular time. So let us just write that. Set of human beings in a town at a particular time. That is our set or our domain. Let us now see what the first relation for this question is. Our first relation is x comma y such that x and y work at the same place. So let's define our relation x comma y ordered pair such that x and y work at the same place. Okay, That is our relation. We have to check its reflexivity, its symmetry and its transitivity. So let us start with the reflexivity. Okay, stating the condition, the most important thing to do, reflexive. Underline it, highlight it however you want. Second most important statement, let x comma x belong to R. Same element ordered pair belongs to R. If x comma x belongs to R, then it implies that x and x work at the same place. Which means it implies that x belongs, it just implies that they are the same person, right? So obviously they'll be working at the same place. That makes the relation reflexive. So, implies x and x work at the same place. Implies that relation is reflexive. Well, now we've just proved the reflexivity of our question. Moving on to the symmetry of our question. If we have to test the symmetry, what do? We take an ordered pair with two different elements and we prove the symmetry of those two elements. So, stating the condition, symmetry, highlight it however you want. Second most important statement in this condition, let A comma B belongs to R. This is one of the most important statements when you do and when you prove the reflexivity or equivalence of a relation. Okay. Now, since A comma B belong to R, they must satisfy the condition that is there. So, this implies that A and B work at the same place. Now, if A and B work at the same place, then however we address them, they will be working at the same place, right? Which means that it implies B and A also work at the same place, right? Right? So, what does this imply? This implies that ordered pair B comma A also belongs to R. Now we have just proved that our relation R is symmetric, haven't we? That proves the symmetry of our relation. Moving on to transitivity. Now, for transitivity, our condition is that if we take two ordered pairs A comma B and B comma C, if both of them belong to R, then it should imply that A comma C also belongs to R. And obviously, if we look at the question and if we look at the condition that has been given to us, X and Y work at the same place, then I think it is pretty obvious that this relation is transitive, because if A and B are working at the same place, B and C are working at the same place, then it implies or it is obvious that A and C work at the same place, because B cannot be working at two different places at the same time, right? So, writing our condition, transitive. You can write transitive, you can write transitivity, you just need to write the condition that you are proving, highlight it however you want, it should be visible to the examiner. Transitive, an important statement comes back again, let A comma B belong to R and B comma C belong to R. Okay, then this implies that A and B work at the same place. And now we won't put another implies sign, we will write and B and C work at the same place. Okay, now after that we will again put an implies sign and we'll write this implies that A and C also work at the same place. Right? So, if A and C work at the same place, they satisfy the condition This implies that A comma C belongs to R, implies that our relation is transitive. That is how we prove that a relation is reflexive, symmetric and transitive. Now, I think that in this question we have also proved one more thing. If a relation is all three conditions satisfied, it is reflexive, it is symmetric, it is transitive, then I think we know what to call that relation, right? You're right, it's an equivalence relation. So this relation, x comma y, such that x and y work at the same place, is an equivalence relation. I'm sure that's clear to you now. Moving on to some more questions. Let's see. Okay. Okay. Up until now, we have been proving that a relation is reflexive, symmetric or transitive. Let's do a question where we have to prove it is neither reflexive nor symmetric nor transitive. Okay. So we know if the question is saying prove, we know that it is not reflexive, not symmetric, not transitive, which means that we have to do our process in a way that we come to the result neither reflexive nor symmetric nor transitive. If a question says check, it means that we don't know if the relation is reflexive, symmetric or transitive, which means that we have to show our working in a way that the examiner knows that we are checking it. We are not proving it. We don't know whether it is reflexive, symmetric or transitive. Okay, let's begin this question. Question number 2 of our exercise, exercise 1.1. Let's go on to that question. Question number 2. Okay. Now question number 2 states that show that the relation R in a set R of real numbers. Now R is a relation, R is a set of real numbers. So do not get confused. Do not use them interchangeably. R set of all set of all real numbers, and R is also our relation. For the sake of simplicity, I will be taking this as R dash so you don't get confused. Now, what is our relation? Our relation is that A comma B such that A less than or equal to B squared. This is our relation. Now, before we begin a question, the first thing we should do is mentally calculate if the question is, if what we are trying to prove is there. You need to think about if the question, you can't just waste your time writing the question down and then going with the flow of the question, because that takes time. So when you're given that 15 minutes reading time, when you go through the questions, get an answer built up in your mind so that when you reach that question, you will be like fatafat write it down, and then you can move on to the next question, which is if it is comparatively more difficult. So first we'll see if it orally if this is reflexive, symmetric or transitive. For reflexive, same ordered pair element belonging to R. Now our condition is this: A is less than or equal to B square. Now I think it is pretty obvious that if A is a number, we are taking A comma A belongs to R, then A cannot be less than equal to A square, right? Because it is the same number. A number cannot be less than equal to its own square. Relation is not reflexive. Coming back to the symmetric, if A comma B belongs to R, and then we know that A is less than equal to B square, then B can definitely not be less than equal to A square if it is already greater than, and it has been proved by the relation itself. So that denies the symmetry. For proving the transitivity of a question, of this particular question, let's take, say, an example. Okay. Let's take 1 comma, oh no, let's take 3 comma 2, and then let's take 2 comma 1.5. Okay, real number belongs to the domain. Okay, we can take that, right? Now 3 is less than equal to 2 square, right? 3 is less than 2 square. This proves the question. Now 1.5 square is 2.25, right? And 2 is less than equal to 2.25. Now if we take this example, we can very easily see that this is less than that and this is less than that. But 3 and 1.5 cannot belong to R because 3 is greater than 2.25, right? Now, if it is greater than 2.25, then it defies our previously mentioned condition. If it defies the condition, it is not transitive. So, 3, 2.25 do not belong to R. The method of writing the questions is same, and that is how you will be proving this question as well. Moving on to another question. Okay. Now this is a question that is somewhat of an easy question, but I'll be doing it. Check whether the relation R defined in the set 1, 2, 3, 4, 5, 6 defined as R A comma B such that B equals to A plus 1 is reflexive, symmetric or transitive. Now if you have to check, we have been given the domain, let us form our relation first. Okay, question number 3. Now let us form our relation first. A comma B such that B equals to A plus 1. Right? That is our relation. Let us form it. R equals to 1 comma 2, 2 comma 3, 3 comma 4, 4 comma 5 and 5 comma 6. I am sure all these elements satisfy the above given condition. Right? Moving on, now we have to check, which means we do not know that these are reflexive, symmetric or transitive. But I am sure the relation that I have written just now, I am sure you can prove it through that. First up, reflexivity. 1, 2, 1, 2, 3, 3, 4, 4, 5, 5, 6, 6. Neither of these ordered pair belongs to R. It is not reflexive. Okay? Symmetry. 1, 2 belongs to R. But I don't see a 2, 1 belonging to R. I'm sure you don't either. So, not symmetric. So, our reflexive condition has not been fulfilled. Reflexive, no. Symmetric, no. Let's check for transitivity. 1, 2 belongs to R. 2, 3 belongs to R. But 1, 3, I don't see it there. I am sure you don't see it either, right? So, it is not transitive either. There you go. Now, I have shown you the pattern as to how to write it. So, you will be writing it in the exact same way. Okay. Moving on to another question. There are similar questions in this exercise. And I'm sure if you... Okay, let's do this one question. Let L be the set of all lines in the xy plane and R be the relation in L defined as R, L1, L2. L1 is parallel to L2. This is a good question. Let's do it. This is question number 14 of your NCERT exercises. And I will be doing the first part which is mentioned, proving the equivalence of this relation. Okay, R is an equivalence relation. I'll just show you how. Reflexive condition. Let L1, L1 belonging to L, or you can write R as well because R is a relation. Okay. Now L1 is parallel to L1. This implies that L1 is parallel to L1. Now any line is parallel to itself. That is a given. So this implies that R is reflexive. Okay. Symmetric. Let L1, L2 belonging to R. If they belong to R, implies that L1 is parallel to L2. Now if one line is parallel to the other, then the other line is also parallel to the first one, right? It's like if the first is parallel to the latter, then the latter is parallel to the former. So L2 also parallel to L1 implies L2, L1 belonging to R. Now checking for the transitivity. Let L1, L2 and L2, L3 belonging to R. This implies that L1 parallel to L2 and L2 parallel to L3. Now if one line is parallel to the other and that line is parallel to the other, then this line will be parallel to the first one. That is a given. So L3 parallel to L1 or L1 parallel to L3 implies L1 comma L3 belonging to R. This proves that our relationship satisfies all three conditions. It is reflexive, symmetric and transitive, which means that it is an equivalence relation, and we have proved it. This question is also famous as a case study based question. So go through it. It is important. Thank you. Have a nice day. If you have any doubts, please let me know in the comments section, and I will be sure to reach out to those doubts in the next video. Ta-da! Bye-bye. Also, if you like my video, please don't forget to like, share, comment and subscribe. Ta-ta!